In this video, we'll troubleshoot some performance issues. We'll cover boost specifically in another video, but the topics in this one can be applied to flows with or without boost applied. We'll cover the most common examples including WAN loss, use of high throughput link bonding mode, MTU mismatch, network or port scanner activity, and ECV resource starvation. Degraded performance for users can manifest in a number of ways, such as connections succeed, but throughput is slower than usual, connections succeed but no or partial data can be downloaded, or connections fail intermittently. We're going to make some assumptions about the LAN, and focus here mainly on WAN side issues, but it is worth noting that sometimes LAN side issues can be the root cause of performance problems. For example, where Wi-Fi is used, congestion or weak signals are common causes. But even if it's a wired connection, broadcast storms or overloaded trunk ports can also play a part. Traceroute can help identify basic issues, and also the scoping questions can help zero in on localized problem LAN infrastructure. So with the LAN side investigated and ruled out, let's begin by scoping the issue. For any performance problem, these are the questions to ask. What is the nature of the problem? Is it happening now? And if not, what was the date, time zone and duration of the incident? If it is slowness, what was the baseline for normal performance? How many users are affected? If more than one user, is it restricted to just one site, or are many sites affected? Is just one server or service affected, or is it many or all services? Are those services located in one place, or many server locations? Is the problem experienced via internet breakout, third-party tunnels, or internal SD-WAN fabric tunnels? Once you know the scope of the issue, you can then begin troubleshooting in a targeted and structured way. The most common cause of degraded performance is, of course, WAN loss. But surely my EC appliance compensates for loss, right? Well, yes, to a point. FEC is forward error correction, and is the mechanism we use to mitigate WAN loss. It's a bit like RAID, but for networks. The default maximum amount of FEC that we put out onto a WAN circuit for non-real-time overlays is 20%, or 1 in 5 packets. Much more than that, and you could actually make your situation worse, since you're consuming more bandwidth by adding more FEC packets. This is one of the many reasons why multiple WAN circuits make your SD-WAN so powerful. See some minor loss on a circuit? Correct it with FEC. Is another path better? Dynamically and instantaneously use it instead. This is what high-quality link bonding mode does, continuously. Perhaps there is no other path available. Maybe this is a small branch site with just one WAN link. What will users report? Probably throughput slower than usual to all other sites and services, both internal and internet-based. With these symptoms, the issue is likely local to the site the users are on. However, if users report throughput slower than usual to a server at just one other site, the issue is more likely to be at that other site. You can check for loss with the Loss Trends report or Live View, and if you see post-FEC loss present, this means the loss was severe enough that the appliance could not completely compensate for it. If all tunnels are affected, you can check that you aren't overrunning the WAN, or investigate issues on the WAN circuit with your provider. If only a few or one tunnel is affected, perhaps the issue is on the other remote site's circuit. The Loss Trends report will show you both sides of the tunnel. If many tunnels are affected over there, then investigations should focus on the WAN circuits and routers there instead. One of the most common causes of degraded performance is using high throughput link bonding mode. The symptoms here may not affect everyone at all sites and might be tricky to nail down, as there won't be any errors or even any observable loss over the WAN. What is common is that a user or users might report that throughput is slower than usual or choppy, and only to a service or site across the SD-WAN. We have a dedicated video on this topic called Why High Throughput Link Bonding Policy Could Cause Performance Degradation on our YouTube Airheads channel. It goes into great detail about bonding and load balancing WAN links with differing characteristics and its effect on TCP-based applications. The short version is, use high-quality mode for all non-real-time user overlays. It will provide users with the best possible network experience and make best use of all available bandwidth. Next up are MTU-related issues. Usually MTU is negotiated end-to-end, but there are a few situations where this does not happen successfully, primarily on PPPoE links or third-party VPN tunnels. Users may report symptoms such as their internal SD-WAN fabric services are working great, but internet access isn't. When you investigate, you might find things like Outlook reports it's connected to Exchange but doesn't download mail, or the internet browser reports connected but waiting for a response forever, or the browser might part load a page with images missing. What is happening here is large packets are being dropped due to an MTU mismatch. Again, there will be no observable loss over the EC tunnels, and the issue would only be seen if you were to run TCP dump where you'd notice TCP segment lost. These symptoms can be verified by running a ping, either from the Edge Connect directly or on the user client PC. For Edge Connect, the commands look like this. If that works, gradually increase the value 1400 until you see a response like frag needed and DF set. For PPPoE, you may find that 1452 is the optimal value to configure on Config System under Maximum TCP MSS. Note that this value only affects pass-through flows, not SD-WAN fabric tunnels, which have their own MTU settings. This one isn't quite so frequent, but sometimes users may report very slow throughput or connections fail completely. They may report this at a specific time of day. On your orchestrator, examine Monitoring Flows Appliance Trends. This report will show you flow counts over time. See if there is a correlation between the time users report the problem and an unusual spike in flow counts. Another observable metric may be loss, not on the tunnels but under Support Dropped Packet Trends on the orchestrator. Again, see if you can correlate loss at the time users reported, specifically the metric LAN RX queue full. This indicates that the receive queues on the LAN interface are full. This should not happen during normal operation, and if seen with a spike in flow counts, is a strong indication of port scanner or other scanning traffic. You may be able to identify it from the top talkers report if it is sourced from a central server, or possibly if it's a rogue client. Finally, a virtual Edge Connect specific issue here. If you have your ECV installed on a hypervisor with multiple other VMs, it's important to ensure that your ECV VM has enough resources to be able to function. The ESXi hypervisor, for example, can ensure this by way of resource reservation. Essentially, you configure the ECV VM settings to reserve all configured CPU and RAM resources, such that in the event that the hypervisor host resources are fully utilized, the ECV can still get what it needs to process flows. But what happens if you don't reserve these resources? Well, this depends, of course, on how severe the hypervisor host resources are being contended for by other VMs. But all users whose traffic is being handled by the affected ECV might report symptoms such as general slowness, slower web page loads, slower throughput on file transfers, possibly even garbled audio quality on voice calls. If you examine the orchestrator reports, you will not see any tunnel loss above anything that may be usual. The internal drop trends graph will also report clean, or at the very least nothing that deviates from baseline readings. Even the appliance CPU usage report will appear to just report lower CPU utilization. However, you may note that the appliance UI is sluggish. In this lab environment test, we simulated contention by setting the VM CPU limit to 1 GHz. This is the same sort of thing that would happen if the hypervisor CPUs are maxed out and the EC doesn't have its resources reserved. Watch how the file transfer speed drops as the EC is starved of the CPU it needs. Now we'll remove the limit and reserve the CPU and memory to maximum. For CPU, it's number of ECV VM cores multiplied by host CPU clock speed. It's really important to always set your ECV resource reservations to the full amount for both CPU and RAM. Other metrics which can help pinpoint the issue include the overall hypervisor CPU and storage utilization. VMware vCenter Server will give you finer detail than we see here, but even in this standalone ESXi example, you can see here the CPUs are working quite hard. If we select the two ECV VMs and hover over the graphs, we can see that they are responsible for the vast majority of CPU utilization. If you're running Boost, you'll also want to pay attention to the storage metrics. Here we can see disk latency rises up, and this causes a bottleneck for network memory, resulting in slower and choppy throughput. Finally, pay close attention to the System Requirements document, which details the minimum CPU cores and RAM for ECV. This can and does change from time to time, so when it comes time to upgrade, refer to the document to be sure you have enough resources allocated. Ideally, give your ECV headroom by allocating and reserving more than the minimum RAM. At the time of recording, the minimum is 8 GB RAM. If you have the resources available, give your ECV 16 GB, and it will be better able to deal with unexpected network conditions, such as slow devices, which by their nature consume more buffer space in RAM. It may not be lost on you that a lot of the symptoms for the scenarios we just discussed are pretty similar. Troubleshooting performance is certainly not easy, but hopefully this guide has given you some clues and some things to check to help your diagnostic process. And that's all for this video. Thanks for watching.